Hello friends, welcome to this fifth video on number theory. This video is going to talk about the divisibility and GCD, that is the common divisor of integers. Come on, first we will check what is meant by the definition for divisibility and how the concept can be extended for finding the greatest of the common divisors. Definition: divisibility. Let a and b be two integers such that a is not equal to 0. Then the following statements are going to be one and the same. We can call like a divides b, a is the divisor of b, a is a factor of b is a multiple of a, b is divisible by a, and so on. So what does these concepts mean to us? Which says that there is going to be an integer c such that b can be expressed as the product ac. Okay. Say for example, I say 4 divides 8. So now this takes the role of A and this takes the role of B. So what I can say is I can express this 8 as 4 times of an integer called as C. And we know that this integer is nothing but 2 for us. So, in terms of division, we say that A divides B if and only if the remainder is going to be 0 when B is divided by A, which means it exactly divides the quantity without leaving any remainder. So, what do we mean by remainder? When there are going to be any left out on a particular value on division. Say suppose when I am going to divide 10 by 4. So how many times 10 goes in 4? This goes 2 times. So I have 4 2s are 8. And now on subtraction, I have a leftover called as 2. This quantity is called as the remainder. So when we say that A divides B, then the remainder is going to be 0 for us. So when I divide 8 by 4, I know that 2 times of 4 is 8 and it leaves no remainder for me. Hence, we denote the quantity of A divides B by the symbol A, a vertical line with B, and we pronounce or read this as A divides B. We read this notation as A divides B. Now let us check on some note on the divisibilities. When A and B, A is going to divide B, then minus A is also going to divide B, as I can write my B to be equal to minus A product minus C. So there exists an integer minus C, so that I can express B as minus A times of minus C. So now as we said, I know that 4 divides 8, and I also know that minus 4 divides 8, as I can write this 8 to be equal to minus 4 times of minus 2. So instead of 2, I will be able to find one more integer called as minus 2 that satisfies the relation. If A does not divide B, it is denoted by the symbol A, the vertical line with a slash B. So A does not divide B. This is how we read this. The relation A divides B is going to be reflexive and transitive in the set of positive integers, but not symmetric. Last session we have seen about relations, and when we talk about relations, there are going to be reflexive relation, transitive relation, and symmetric relation. So what do you mean by reflexive relation? If A divides A is going to be true for all the values on the set of positive integers, for all the A belonging to the set of positive integers, then you call it to be reflexive, and hence it is going to be true. We all know that 8 divides 8. This is going to be true, so it is reflexive. What do you mean by transitivity? If A divides B and you have B to divide C, then we will have A to divide C. Now 2 divides 4 and we know that 4 divides 8, in which case we can say that 2 also divides 8. So if this relation is going to be true, you call it to be transitive relation, and we know that, or we can see that clearly the division or A divides B is going to be transitive in nature. So reflexive is true, transitivity is true. But what about symmetricity? Symmetricity is not going to be true, which means that whenever I say A divides B, that does not imply to me B will divide A. I can say 2 divides 8, but is the opposite relation 8 divides 2 is going to be true? No, this is not going to be true. So I cannot say it is going to be symmetric in nature. So the relation of A divides B is not going to be symmetric, but rather it is reflexive and transitive in nature. Next, we will move on some properties of divisibility, which says that if A divides B and A divides C, then A divides B plus C. Like 2 is going to divide 4, 2 is going to divide say 8. This implies 2 divides 4 plus 8, which is 2 divides 12. Yes, that's going to be true. If A divides B and B divides C, then A divides C. This is nothing but the transitive rule which we have seen in the last type. Now, if A divides B, then A divides m times of B for some integer m. That is, if A is going to divide 4, or say 2 is going to divide 4, then you can say that 2 divides multiples of 4. So you can say 2 into 4, which is going to be 8, 3 into 4, which is going to be 12. So 4 into 4, which is 16, and so on. So 2 divides 8, 2 divides 12, 2 divides 16, and so on. The multiples of 4 are all divisible by 2. So if A divides B, then A also divides multiple times of B. Now combining your property number 1 and the property number 3, we can say that if A divides B and A divides C, then A divides MB plus NC. That is the linear combination for some integers m and n. Okay, so these are going to be some properties of divisibility which will help us to solve some simple problems. Next, moving on, we define what is meant by prime number. An integer p which is greater than 1 is called as a prime if its positive divisors are going to be 1 and the integer p itself. So, apart from 1 and the number itself, the number is not divisible by any other quantity, then you call it to be prime. Any integer which is greater than 1 but which is not a prime is referred by the name composite numbers. Okay, so take for the case 3 is going to be a prime number. Okay, how about 4? Now 4 is divisible by this, you call it to be prime because 3 is divisible by 1 and 3 is divisible by 3 alone. Hence, you call the number 3 to be prime. How about 4? 4 is divisible by 1, 4 is divisible by 2, 4 is divisible by 4. So, apart from 1 and 4, there is going to be one more number called as 2 which is going to divide this 4. So, how do you term this number which has divisors other than 1 and itself called by? You call it as composite numbers. A positive integer n is composite if it has a divisor d that lies between 1 and n. That's what we saw over here. Between 1 and n, there is going to be some number that it's going to divide it. Okay. So, say suppose you have 10. So, what are going to be the divisors of, so the integers, how I can write, I can say what are the divisors of 10. You can have 1, you can have 2, you can have 5 which divides 10, and then you will have 10 that divides 10. Okay, so apart from this 1 and n, there are going to be 2 more quantities that is going to divide 10. Hence, this is not going to be a prime, but rather it is termed as a composite number. There are certain points to be noted that the integer 1 is going to be neither prime nor composite, as we see that by the definition itself we start the values from greater than 1. So the number 1, which is the integer, is neither prime nor composite in nature. So as we go on, we find the primes of the integer set to be 2, 3, 5, 7, 11, 13, 17, 19, 23 and so on. So these are the numbers which are going to have 1 and themselves as their divisors and not any other things apart from it. And the next important point to notice, 2 is the only even prime number, because all other even numbers can be expressed as a product of 2. So when they are expressed as a product of 2, you find 2 to be a divisor of it. So none of the prime even numbers are going to be prime apart from 2. And there are going to be infinitely many primes. So they are going to be countless, like going on and on and on until you move towards infinity. Next, we move on to something called as fundamental theorem of arithmetic, which says that every integer n greater than 1 can be written uniquely as a product of prime numbers. So, say suppose I have the number called as 12. How I can express this 12 as? I can express this 12 as 4 into 3. 4 3s are 12. As well as I can express this as 6 into 2. 6 2s are also 12. But these 4, 3, 6, 2 and so on are not going to be expressions as product of prime. So when I do the product expression as a prime factorization, then this 12 can be written as a product of prime in exactly one and only one way. So how I can do it? I can split 12, which goes into 6 times. This 6 again goes into 3 times and 3 goes in 3 one time. So I can express 12 as 2 to the power of 2 product 3 to the power of 1, which is going to be expressed as product of, this is one prime number, this is one prime number, and this way of expressing 12 as a product of prime is going to be unique. What do you mean by unique? There is going to be only one way in which we can do so. Okay, so this theorem is called as the fundamental theorem of arithmetic. Now, as we saw, what is meant by prime factorization? The unique expression for an integer n, where we express it as a product of prime, is called as a prime factorization. So you can split the integer n as p1 power k1, p2 power k2 up to pn power kn and so on, so that each of these pi's are going to be prime, which are raised to some power called as k1, k2, kr and so on, where 1 less than or equal to I less than r. And we can see that this prime composite integer and p is going to be any prime number, then the number of prime for which you will have to find it will always be less than or equal to square root of n. So we will see it by an example. Say suppose we want to do the prime factorization of the number called as 100. How will I express this 100 as product of prime? Let me start with the least of the prime, say 2, which goes 10 goes 2 times and 0 goes 0. So 10 goes 5 times and then you have 0 to go as such. Okay, now 50 goes into 25 times and 25 goes in 5 times. So how I can express 100 as? 100 can be expressed as 2 to the power of 2 and 5 to the power of 2. This way of expressing 100 as product of prime is going to be very unique in nature. Say for example, we have 9999. How I can express this 9999 as it is 9 times of 11 and 101. But this 9 is nothing but 3 square. So I write 3 square into 11 to the power of 1 into 101 to the power of 1, which is again a prime number expressed to the power of 2, prime to the power of 1 and prime to the power of 1. And we know that by the second note, if n is going to be greater than 1 is a composite integer and p is prime, then the prime is going to be less than or equal to n. So if I want to know whether the given number is going to be prime or not, then I can just go for the square root of the number and then check all the primes that are going to be less than or equal to the quantity. Say suppose I want to check if 83 is going to be prime or not. So what will I do? I will have to just go for checking. I need not have to go checking from 1, 2, 3, 4 and so on till 83. So this says that take just a square root of 83. What do you know about the nearest number which is going to be the square root of the term? We know that the square root of the nearest of the number is going to be square root of 81, which we know it is going to be equal to 9. Just check for the prime numbers which are less than or equal to 9. So what are they? 2, 3, 5, 7. So we check that is 83 divisible by 2? No. Is 83 divisible by 3? How to check divisibility of 3? 8 plus 3, 8, 9, 10, 11. Is 11 divisible by 3? No. So it is not divisible by 3. How to check divisibility by 5? 83 divisible by 5. If the last integer is going to be 5 or 0, then it is divisible by 5. It is also not divisible by 5. So is 83 divisible by 7? No. 83 is not divisible by 7. Hence we conclude that none of the numbers which is going to be less than the square root of the number value less than the primes is going to divide it. Hence 83 is going to be a prime. So if we are able to find a number which divides it, then you can very well say that it is going to be composite and hence it is not going to be prime in nature. Next, we move on to the division algorithm. Let a and b an integer and b be a positive integer. A can be any integer, b is positive, meaning it is going to be greater than 0. Then there are going to be unique integers q and r with 0 less than or equal to r less than b, such that I can express a as bq plus r. So first when we say that a divides b, there are going to be no reminders. In the division algorithm, we allow for the remainder, in which case the element a can be expressed as the constant times or the quantity times of b plus the remainder r. The quantities or the integer q is called as the quotient of the value when a is divided by b, and r is referred as the remainder when a is divided by b. Say for the case I am dividing 43 by 5. So what happens? 43 can be expressed as how many times 43 goes in 5? I know that 5 eighths are 40, and when subtracted it leaves a remainder of 3. So I can express this 43 as 8 times of the quantity 5 plus the remainder which is going to be 3. So now 5 eighths are 40 plus 3, 40 plus 3 makes it as 43. In which case this quantity 8 which I have will be called as the quotient when your 43 is being divided by 5, and this quantity called as 3 is called as the remainder when your 43 is being divided by 5. Note that this remainder always has to be between 0 and b. It can leave a remainder of 0 and number which is strictly less than 5. Why so? Because when it leaves the remainder to be 0, 1, 2, 3 and 4, it is permissible. when it leaves a remainder 5, what happens? Actually, the number is divisible by 5 one more time. Okay, so the possible remainders when you divide by any quantity n has to be strictly less than that of n. Okay, so 0 less than or equal to the remainder value will always be less than that of the value by b by which you divided. So keep this in mind. This is called or referred as the division algorithm. Next, moving on, we find what is meant by the greatest common divisor. Given any two integers a and b, an integer d not equal to 0 is referred as a common divisor or a common factor of a and b if d divides both a as well as b. So it has to divide both the quantities a and b. In addition, if this a and b are not both equal to 0 and we say the value d is the greatest of the common divisor if it is going to be the largest of the common divisors for a and b. This GCD or greatest common divisor is also referred by the name highest common factor or HCF. Now let us watch an example like what is going to be the GCD of 24 and 42. The numbers that divide both 24, you need to keep in mind it is both 24 and 42 are plus or minus 1, plus or minus 2, plus or minus 3 and plus or minus 6. Okay, and out of these divisors, 1 is a divisor, 2 is a divisor, 3 is a divisor, 6 is a divisor. And among them, what happens is 6 is going to be the largest of all the quantities. So what do we call this 6 as? This 6 is referred as the GCD of the quantity 24 and 42. Moving on, we say something called as relatively prime. A and B are relatively prime or also referred by the name co-prime if the GCD is going to be 1. Say suppose I am finding the GCD of the number called as 17 and 22. So can you find anything common between them? No number is going to be common apart from 1. So the GCD is 1. So how do you refer these two numbers as? These two numbers are referred as relatively prime or you call them by the name co-prime. And we can see that the consecutive integers are always co-prime. Like GCD of 3, 4 is always 1. GCD of 100, 101 is always 1. So whenever you take two consecutive integers, the GCD is always 1. And now coming to the case where you call it to be pairwise relatively prime. What is meant by pairwise relatively prime? If the values are relatively prime for any combination of pairs you take, then you call it as pairwise relatively prime. Okay, let us consider the example for the case when we have the integers 9, 13, 25. Now consider GCD of 9 and 13. What is the GCD of 9 and 13? 13 is a prime. 9 can be expressed as 3 square. So the GCD is 1. Now GCD of 13 and 25. What is the GCD of 13 and 25? Again it is 1. What is the GCD of 9 and 25? This is going to be product of 3 and this is product of 5. And so there are no common points apart from 1. So what do we call these pair of numbers 9, 13 and 25 as? They are called as pairwise relatively prime. Now for a counter example, let us take the case 10, 17, 25. Now what is going to be GCD of 10 and 17? So this is going to be equal to 1. Now what is the GCD of 17 and 25? This is again going to be equal to 1. But when it comes to GCD of 10 and 25, we notice that apart from 1, the greatest of the number that divides it is going to be 5. So here this quantity is not going to be 1. So these pair 10, 17 and 25 are not pairwise relatively prime. So this is going to be the way in which I can define relatively prime or co-primes and pairwise relatively prime numbers. Now how to find the GCD using prime factorization? Now express the numbers a and b as product of primes, and this can be done in a unique way by our fundamental theorem. Then correct the minimum of the powers of a and b for each of the prime. This gives us the GCD of your number A and B. Say for suppose I have the numbers called as 24 and 36. I want to find the GCD of it. How I can express 24 as product of prime? So 24 can be expressed as 2 will go 12, go 6 times, go 3 times. So I can express 24 as 2 to the power of 3 and 3 to the power of 1. Let me go for 36. When this goes into, this goes 18 times, 2 goes 9 times, 3 and 3. So 36 is nothing but 2 to the power of 2 and 3 to the power of 2. So what will be the GCD of 24 and 36 using prime factorization? So the first element or the first prime is 2, for which we find the minimum of their powers. What are the powers? 3 and 2. Take the product with second prime. What is the second prime? 3, which will be minimum of, what are going to be their powers? It is going to be 1 and 2. So I have 2 to the power of minimum of 3 and 2 is going to be 2, and 3 to the power of minimum of 1 and 2 is going to be 1. So 2 square makes it as 4 and 3 power 1 makes it as 3. So the greatest of the common divisors of 24 and 36 is going to be equal to 12. So this is the way in which we find the prime factorization of the given numbers A and B, finding the minimum of these powers. When one or more of the prime numbers is not present, you can just make the entry for them with a power to be equal to 0. So in which case you can just take what is going to be the GCD of the prime to the minimum of the quantities, which is going to be your 0 and the remaining number. Okay, so the last one to go on with will be the least common multiple. If A and B are positive integer, then the smallest positive integer that is divisible by both A and B, so it is going to be the smallest positive integer that is divisible by both A and B is called as the least common multiple of A and B and is denoted by LCM of A and B. Now the same rule applies over here like our GCD, but the thing is that instead of finding minimum value, what do we go for is going to be maximum value of A and B. So we come to the relationship that connects the GCD and LCM by the factor GCD of A comma B into LCM of A comma B is the product AB. Okay, we will move on with an example and then try to complete it. So let us find the GCD of the number 24 and 30 and LCM of the number 24 and 30, and we will see if the relationship is going to hold true. Okay, as we saw, 24, 2, 12, 2, 6, 2, 3. So 24 is 2 to the power of 3, 3 to the power of 1. How about the number 30? 2, 15, this goes 3, 5. So it is 30, which is expressed as 2 to the power of 1, 3 to the power of 1, 5 to the power of 1. Here the base 2 prime is there, the base 3 prime is there, base 5 is not present over here. So we introduce this base 5 with a power to be equal to 0 because anything power 0 is going to be 1. Now what is going to be the GCD? The GCD is 2 to the power of the minimum of the numbers 3, 1. 3 to the power of minimum of the number 1, 1 and 5 to the power of minimum of the numbers 0 and 1. So it is 2 to the power of 1, 3 power 1 and 5 power 0. So it is 2 into 3 into 1, which makes it as 6. So GCD of 24 and 30 is going to be 6. Whereas let us find out what is the LCM. LCM is 2 to the power of maximum of the number, which is 3 and 1, and 3 to the power of maximum of 1 and 1 and 5 to the power of maximum of 1 and 1. So this gives me 2 to the power of 3, 3 to the power of 1, 5 to the power of 1, 2 power 3 makes it as 8 into 3 into 5. So when we go on with this, this is going to be 8 3s are 24 into 5. So this makes it as 120. So I have got the GCD separately. I have got the LCM of the values separately. And let us verify what is going to be the number 24 multiplied by 30. What is going to be 24 multiplied by 30? 24 into 30 gives me 720. And now what is the product of GCD and LCM of these two numbers? It is going to be 6 into 120. And when I do 6 into 120, I again have this to be the same as 720. Hence what we have proved? We have proved that the GCD into LCM of the two numbers A and B are the same as the product of the numbers A and B. I hope this video has given you a clear idea on the basic concepts of divisibility, the fundamental theorem of your arithmetic, the division algorithm, the GCD and LCM and the relationship that connects these quantities. Happy learning. Keep learning. Thank you.